Here we go. The last unit in the course. I'm just going to do this one right straight through like I did unit 13. So we turn our attention now from the outer parts of the atom that we looked at in section 13. And now we're going to go down into the middle of it and talk a little bit about the atomic nucleus. So it looks like the first thing I put there is a few words about what holds the nucleus together. With the exception of hydrogen, where there's only one proton, there are multiple protons in the nucleus, very close to each other. The nucleus is really small. From one proton to the next is something on the order of 10 to the minus 15 of a meter. And from back at the beginning of the course, where I talked about Coulomb's law, like charges repel. And the force is proportional to 1 over r squared. So the closer you get, the bigger the force is. Since the protons are really, really close, there's a really, really significant amount of force trying to pop the nucleus apart. They all want to be pushed away from each other, and yet the nucleus does not pop apart. So there must be some other force that's even stronger than Coulomb's law repulsion holding the nucleus together, an attractive force. And this attractive force has been given the appropriate but not very creative name of the strong force. A strong force acts on both protons and neutrons. Electric charge has nothing to do with it. It's basically, the conventional way of looking at things is to say that there are 4 basic forces in nature. There's gravity, there's electromagnetism, the strong nuclear force, and the weak nuclear interaction. Almost everything you encounter in everyday life is electromagnetic, okay? If you're walking down the hall and somebody bumps into you, that is ultimately an electromagnetic force, because the electron clouds in the atoms on the surface of your shoulder come into contact with the electron clouds in the atoms on the surface of the other person's shoulder, and like charges repel. So you can't push these 2 negatively charged clouds of electrons through each other. These atoms are almost entirely empty space. It's not like these things are solid objects that bounce off each other the way you imagine balls on a pool table bounce off each other. There's actually more empty space in an atom than there is in the solar system. The diameter of the sun is only a few hundred times smaller than the diameter of the Earth's orbit. In a hydrogen atom, the diameter of the nucleus is 100,000 times smaller than the diameter of the electron's orbit when it's in the ground state. And so yeah, atoms are almost entirely empty space. But when 2 objects encounter each other, the electrons in the outer part of the atoms repel each other, and that's where friction forces come from. That's where any kind of contact forces come from. So most of the forces you encounter are electromagnetic. When you jump up in the air and come back down again, that's gravity. And that pretty much accounts for everything. You don't really encounter the strong force in everyday life unless you want to count the fact that your body doesn't drift apart immediately into a bunch of separate protons and neutrons and things. But the strong force has a very short range. Basically, it operates within the atomic nucleus, but its strength falls to 0 at distances any greater than that. It doesn't even reach into the outer part of an atom, let alone across the distance to another nucleus, or let alone anything you can perceive, just walking around poking at things. So within the atom, though, when protons and neutrons are in close proximity, it is strong enough to overcome Coulomb's law of repulsion and hold the thing together. The number of protons in a nucleus is what determines which chemical element you're talking about, because the charge of the number of protons determines the charge of the nucleus, and the charge of the nucleus determines how many electrons it attracts into orbit around it. How many electrons are orbiting around the nucleus determine all of its chemical properties. The electron structure is where all the, not only the chemical properties, but the optical properties, that's where everything comes from. So hydrogen is 1 proton, helium is 2 protons, lithium is 3 protons, and on down the list. The same number of protons, though, can be matched up with different numbers of neutrons. Every element there is has multiple isotopes, is the word that's used for it. The different nuclei of a given element. Same number of protons, different number of neutrons. And as an example, I wrote, and this also introduces you to some notation, I wrote out here the 3 isotopes of hydrogen. As you've probably heard, your body contains more water than anything else. I mean, there's a lot of other stuff in there too that makes you more interesting than a bucket of water, but there is a lot of water in you. Water contains an oxygen and 2 hydrogens, and the vast majority of the hydrogen atoms in your body, there's hydrogen in other things like proteins and fats and things too, the vast majority of the hydrogen atoms in your body is this isotope here. It's like, don't quote me, but I want to say the natural abundance on Earth is that it's about 1 out of every 6,500 hydrogen atoms is of the heavy type. So the vast majority have a nucleus that consists of a proton. Number on the bottom is the atomic number. That means how many protons are in the nucleus. That's actually redundant with the chemical symbol. Okay, 1 proton means the same thing as hydrogen. And so sometimes you see that bottom number left off. But if you don't happen to be a chemistry major and you don't happen to have memorized, I mean, even us physics majors haven't really memorized the whole periodic table. I'd have to look up the atomic number for tin. I don't know it off the top of my head. So when a chemist is writing something for some less educated person like me, they stick the bottom number on there if it's something you're going to need to know. But that means the same thing as hydrogen, 1 proton does. The number on top is called the mass number. That's the total number of particles in the nucleus, protons plus neutrons. Protons and neutrons have approximately the same mass. Neutrons are actually just a little bit heavier. But if you're not being too careful about your level of precision, you can use the mass of a proton or a neutron as a unit of mass, which is a lot more convenient than working in kilograms, because it would always be really tiny numbers if you worked in kilograms. So anyhow, the total number of particles in the nucleus gets called the mass number because it's approximately the mass of the nucleus in atomic mass units, defined a little further down the page where you can't see it yet. So anyhow, 1 out of every 6,500, if that's the correct number, of the hydrogen atoms in your body and elsewhere, like the Pacific Ocean, contains a proton and a neutron for a total of 2 particles. We in the trade call this deuterium, and it's also a stable nucleus. Just doesn't happen to be as much of it around. If somebody wants to know the reason for that, we'd have to get into a discussion of what happened during the Big Bang, and that would definitely be going off on a tangent. And then there's tritium, where the nucleus contains a proton and 2 neutrons for a total of 3. Tritium is not a naturally occurring substance because it's radioactive and has a half-life of something like, give or take a few years, it's somewhere in the neighborhood of 15 years. So very short compared to the lifetime of the Earth, not something that's still laying around from the beginning. But small amounts of it were found in the environment, especially in the mid-20th century, because tritium is great stuff if you want to build a hydrogen bomb. So back in the good old days of above ground nuclear testing, very small amounts of tritium escaped into the environment. Most of it would have decayed away by now. But you see these heavier isotopes fuse with each other more easily than light hydrogen does, which makes them a preferable fuel for a thermonuclear device. So yeah, if the guys at the airport catch you with a little bottle full of tritium, yeah, you're in a lot of trouble. But anyway, I don't know how they would know that it was tritium just by looking at it. If there was a Geiger counter, they'd probably pick up on the fact that it was radioactive. Little tip here for anybody who's thinking about it, probably better not to go through Air Force security with anything that's radioactive. That might delay you a little bit in your flight. So anyhow, every element in the periodic table has multiple isotopes like this. And what they mean, once again, is same number of protons, because that's what defines what element it is. That number of protons can be matched up with different numbers of neutrons that make some isotopes a little heavier than others. So this is just a quick little exercise in understanding the notation. We have a nucleus of lead-208. And the question is, how many neutrons are in there? Well, if the number on the bottom is how many protons, and the number on top is how many protons plus neutrons, subtracting them would give you the number of neutrons. And that comes out 126 for that. Lead probably has something like 15 different isotopes, if you count all the unstable ones. Okay, once I move the thing up so you can see the rest of the page, the next topic is binding energy. Binding energy is kind of what the name says. It's the amount of energy that holds a nucleus together. In other words, how much energy would you have to supply if you wanted to pull it all apart into a bunch of individual protons and neutrons? Well, this gets into the equivalence of mass and energy from the special theory of relativity. If you took Physics 121, we did a very brief introduction to special relativity. There's a lot that was left unsaid, but right at the end of the course, that was section 14 of that course. But if you didn't, basically it comes down to this. It turns out, when you get into 20th century physics, that mass is a form of energy, okay? If you start listing out different kinds of energy, there's kinetic energy, there's potential energy, there's chemical energy, there's thermal energy, one of the things that belongs on that list is mass, because in certain types of processes, energy can be made into mass, mass can be made into energy. So if one can be made into the other, they're basically the same thing. The amount of energy that's equivalent to a certain amount of mass, well, you've probably seen this one before. It's like on all the physics nerd t-shirts, E equals mc squared. M is the mass, c is the speed of light in a vacuum. So if you have 1 kilogram and could somehow convert it entirely into energy, speed of light is 3 times 10 to the 8th, if you're measuring in meters per second. Squaring that gives you 9 times 10 to the 16th. So 1 kilogram times 9 times 10 to the 16th would be 9 times 10 to the 16th joules, which is a lot of energy. A little bit of mass goes a long way. Well, that's kind of what's going on with this formula for binding energy. Focus. That didn't work. Let's try it again. I must have done it too fast or something. Or maybe the camera's just feeling ornery. Oh, I don't know what I did, but I'm glad I did it. Okay, so if you have a brick laying on the ground and you pick it up and lift it as high as you can reach and maybe put it on a shelf up there, you added some potential energy to that brick. That potential energy is equivalent to some mass. So sitting up on that high shelf, the brick is actually slightly heavier than it was when it was laying on the floor. Well, it's only, you know, compared to a kilogram is 9 times 10 to the 16th joules. If you give a brick, I don't know, 10 or 20 joules worth of energy, that is not really a measurable change in its mass. But if you start taking atomic nuclei apart, you're dealing with some really strong forces acting on a fairly small amount of mass. And so as a percentage of the amount of mass that's there, it becomes a significant thing. So to pull a nucleus apart, you have to do work against the attractive forces, okay? You have to pull against the strong force whenever you pull a proton or a neutron out of a nucleus, you know, kind of like pulling a bunch of Legos apart. You have to do work against friction. Pulling a nucleus apart, you have to do work against the strong force. Adding energy to those particles as you do this makes them slightly heavier. And with sensitive instruments, the difference in mass can be measured. So the binding energy would be, if you have the mass of the entire atom and you separate it out into a bunch of individual neutrons and a bunch of, well, individual protons. Actually, this stands for the mass of a hydrogen atom, because each hydrogen atom would have an electron. That takes care of the mass of the electrons that way also. So anyhow, if you take, the idea is, if you add up the masses of the individual pieces of an atom, it adds up to a little bit more than when the atom is all put together. The difference being the amount of mass that's equivalent to the binding energy. Just like the brick is a little heavier when it's sitting on a high shelf, a neutron is a little bit heavier when you pull it out of an atom, because you have to add some energy to pull it out of that attractive force that was acting on it. So it would be the difference in the masses times the speed of light squared, except, as I've mentioned, when you get into atomic work, people don't generally do energy in joules, and they don't generally do mass in kilograms. They do mass, they do energy in electron volts, or in this case, it would be millions of electron volts, MeVs. And a convenient unit for mass is one that's approximately equal to the mass of a proton or the mass of a neutron. The exact definition is it's 1/12 the mass of a carbon-12 atom. And that's called an atomic mass unit. And it's, you know, equal to a little tiny fraction of a kilogram. The conversion factor is in your handout. So what this 931.5 is on the end here, that's the speed of light squared together with the conversion factors from joules to MeVs and the conversion factor between atomic mass units and kilograms. So let's see, the mass of a hydrogen atom is this, the mass of a neutron is that. Those numbers would be available on your formula sheet also, so you could use them in this relationship. And let's see, the last word kind of goes off the edge of the screen there. Last couple of words. What I want you to do now is stick numbers in this equation. Before you go pausing it, binding energy per nucleon is not quite what this is. This is simply the binding energy of the nucleus. What is sometimes a useful thing to talk about is the amount of energy per particle. A nucleon just simply means the particles in a nucleus, okay? One day somebody had just used the phrase protons and neutrons for about the 35th time, and it was only 10 o'clock, you know? And they said, you know, wouldn't it be easier to just have a single word for that instead of going around saying protons and neutrons, protons and neutrons, protons and neutrons all the time? And so a nucleon is any of the particles you find in a nucleus. So protons and neutrons. So the energy per particle, the energy per nucleon would be to take the binding energy, and in this case, you would divide it by 16, is what that's asking for. So yeah, here's where you pause it and stick numbers in this and see if you get that. So this nucleus contains 8 protons. You can tell that because the number on the bottom is 8. And that's the number you put in for Z. Z is the atomic number. Times the mass of a hydrogen atom. This is not one time when this is not a situation where it would be a good idea to round off to 3 significant figures. If you round everything off to 3 significant figures, you're just going to get 0 for the answer, and that's not right. You need to carry more decimal places, kind of like this. So the atomic number times the mass of a hydrogen atom. N means the number of neutrons. 16 minus 8 is 8. Subtract, just like in the question about the lead atom a few minutes ago. Mass of a neutron actually just a little bit heavier, 1.008665. So that and that is what the masses of all the individual particles would add up to if you separated them. When you have them all put together in an oxygen atom, the mass is 15.9949. Then there's the 931.5 MeVs per atomic mass. This basically says how much energy corresponds to how much mass. 931.5 MeVs per atomic mass unit. So the binding energy comes out, well, let's actually, I'll write out the intermediate step. in the brackets, that's 0.137005. That's kind of interesting to look at because that shows you that it's actually a little more than an eighth of an atomic mass unit that, you know, the difference between having the nucleus apart and put together. You let all these protons and neutrons touch and stick to each other, and a little bit more than an eighth of an atomic mass unit worth of energy, worth of mass disappears. It's converted into energy, probably given off as some photons, I'm pretty sure. I mean, the mass of an electron is only about roughly 1/2000th of an atomic mass unit. So if you've got a difference of an eighth of an atomic mass unit, well, you know, on the atomic scale of things, that's a significant amount of mass that disappeared on you there. So anyhow, that many atomic mass units times the 931.5, and you get 127.6. EB for binding energy, B for binding. But the question asked for the binding energy per nucleon, which is a good measure of how tightly bound together the nucleus is. For most nuclei, that number is somewhere in the 7.5 to 8.5 range, or not too far outside of there anyhow. We go. Next topic is radioactivity. One day in the 1890s, I remember exactly what year it was, but I'm sure it was in that decade. There was this guy named Becquerel. I think Henry was his first name. I believe he was French, if I remember right. Anyhow, whatever country it was he was living in, he had a drawer where he was keeping some photographic plates, basically film, and he also had some rocks in there that was uranium-bearing minerals. And well, we don't need to get into the experiment he intended to use these rocks and these photographic plates for. The important part of the story is that when he went to use I kind of hesitate to call it film because it was actually on glass plates, I think, rather than being conventional film like you would picture film, but might as well call it film because that's what everybody's familiar with. He went to use his film and he found it was already exposed. And he was really, really sure, he was feeling pretty confident he hadn't let any light get on his film. So he kind of looked into that, and it turned out that there were some kind of rays coming out of his rocks that nobody'd ever known about before. And subsequent investigations by him and other people like Pierre and Marie Curie played a very large part in this sort of thing. Over the next few years, it was determined that there are actually 3 different kinds of rays that can be given off by a nucleus. This isotope gives off this kind of rays, that isotope gives off that kind of rays. A lot of nuclei actually give off more than one, but they were named with the first 3 letters of the Greek alphabet. in terms of their penetrating ability. Alpha, beta, and gamma, first three letters of the alphabet. Alpha rays were the least penetrating. You could block them out with, a couple sheets of paper. It'd be all it took to block some alpha rays. Beta rays were more penetrating. You might need something like a millimeter or two of aluminum or some substance like that to block out most of them. And gamma rays were the most penetrating. That's where you start needing the lead bricks, if you want to protect yourself from gamma rays. Incidentally, if you're exposed to gamma rays, just in case anybody was wondering, no, you do not turn into the Incredible Hulk. You just die. Well, depending on the level of exposure. If it's not that strong of an exposure, then you lose your hair, you throw up for a few days, and after a few weeks you get better. But yeah, if you take a really serious, and by the way, being bit by a radioactive spider does not turn you into Spider-Man either. But anyway, alpha rays. The story with alpha decay is this. I mentioned back up at the top of the page when I was talking about the strong force that it has a very short range. So short that if you get the larger nuclei that are toward the end of the periodic table, atomic numbers of like 90 or 100 or something like that, the range of the strong force is so short that it doesn't even extend from one side of the nucleus to the other, let alone beyond it where you might directly perceive it like you do gravity. So basically, each proton in a nucleus is held in place pretty much by its nearest neighbors. You get farther away, the strong force gets not so strong at all. The Coulomb's law force, on the other hand, has, if you're talking about atomic distance scales, the Coulomb's law force effectively has an infinite range. Every single proton in the nucleus repels every other proton, but the protons are only attracted to its nearest neighbors. Well, once you get a big enough nucleus that a given proton is completely surrounded, it's not going to get any more nearest neighbors than that. And so as you work your way down the list towards bigger and bigger nuclei, the attractive force that holds the nucleus together levels off, while the repulsive force from Coulomb's law keeps getting bigger and bigger as you add more and more protons to the nucleus. The last stable element is number 83, bismuth, the stuff that's in Pepto-Bismol. Beyond there, they are all radioactive because Coulomb repulsion wins, okay? With a nucleus that's too big, the strong force cannot overcome the Coulomb's law force and protons go popping out, except 2 protons and 2 neutrons stuck together is a lower energy configuration than popping them out individually because of the binding energy of the 2 protons and 2 neutrons. So that's what an alpha particle is, okay? The so-called alpha rays turned out to be a bunch, turned out to be particles being shot out by the nuclei. And the particles are nuclei of helium-4, 2 protons and 2 neutrons stuck together. I kind of abbreviated here, P for proton and N for neutron. So typical example, one of many alpha sources is uranium-238. It spontaneously decays into thorium-234 plus an alpha particle, a nuclear. Now, the term alpha particle does not refer to just any old helium nucleus. A nucleus of helium-3 or helium-5 is not an alpha particle. An alpha particle is helium-4. Notice, mass numbers add up to the same thing on both sides. You had 238 units of mass before. Well, a little bit of difference in the mass because of the binding energy, but the mass numbers are sort of a rounded off thing compared to, you know, instead of 1.007825, the mass numbers are just rounded off to 1. And so the little bit of a difference in the binding energy doesn't show up. If you have 238 units of mass before, you got to have 238 units of mass afterward. So 234 plus 4 adds up to 238. Likewise, electric charge must also be conserved. If you had 92 units of charge before, you have to have 92 units of charge afterward. 90 plus 2 equals 92. So if I was to give you a question where there was a decay like this written out, and I left some blanks and told you to fill in the numbers in those blanks, that's how you would figure it out. If I'd left a blank right there, you would say, oh, well, let's see. 238 minus 4 would be 234. I should put 234 in there. Turn the page. Top of the next page, beta decay. Basically, the 3 different types of decay we're talking about, alpha, beta, and gamma decay, correspond to the 3 different forces that operate on the atomic scale: the strong force, the weak force, and electromagnetism. Gravity is basically non-existent when you're doing atomic physics because the particles you're talking about have so little mass that gravity is many, many, many times smaller than the other forces that are acting. So the alpha decay involves a failure of the strong force. The strong force is supposed to hold the nucleus together, and when it doesn't, you get alpha decay. So alpha decay is kind of a strong force thing. Beta decay involves the weak interaction. Without getting into too many details, the weak interaction isn't, I mean, quite often the way it manifests is not exactly in creating a force between particles. I guess you could look at it this way. Force changes an object's momentum, okay? If you've got a ball flying along and some force like gravity is acting on it, it's going to make the ball change direction. Its momentum will be in a different direction than it was before. Or if a ball runs into another ball on a pool table, the collision force changes the momentum of the ball. Well, sometimes the things that we rather loosely call forces change a different property of a particle rather than its momentum. And one thing that a weak interaction can do is change a neutron into a proton and an electron. Or to be precise, it changes one of the quarks within a neutron into a different kind of quark and an electron. So that's what goes on during beta decay. Now, the particles in a nucleus have energy levels, just like the electrons orbiting around in the outer part of the atom have energy levels. The particles in the nucleus also have energy levels. If you have, for example, something like carbon-14, 6 protons, 8 neutrons, 14 minus 6 is 8. So they're stacked up in energy levels, and the neutron with the highest energy looks down and says, you know, if I was down there, I could have a lower energy than I have up here. Physical systems want to they want to minimize their energy. You know, water wants to run downhill, and you know, things in general like to go to wherever it is they can have the least energy. I sometimes feel that way myself, especially early in the morning when I've just gotten up. It's like, I just want to minimize my energy. I want to sit here for a little while. Anyway, The neutron says to itself, if I was a proton, I could be down there in that proton energy level that nobody's using, instead of stuck up here in this higher energy neutron state that I'm in. Well, I think I'll do it. And so it changes itself into a proton by giving off an electron, and down it goes. This is the reason why stable nuclei have something fairly close to equal numbers of protons and neutrons. Okay, the lighter elements, like carbon, the ones up near the beginning of the periodic table, they usually have pretty close to exactly the same numbers of protons and neutrons, like nitrogen 14. 7 protons, 7 neutrons, nice and even. You get down toward the bottom of the periodic table, and there tend to be some extra neutrons, because you see, neutrons take part in the strong force, but they aren't involved in electromagnetism because they're not charged. So you get into the heavier nuclei, and a few extra neutrons help hold it together against alpha decay. So it's not, even then though, it's only a few extra neutrons. Well, you get all the way down to like element number 100, and you've got like 100 protons and 150 neutrons, something in that general neighborhood. But you never find a nucleus with 100 protons and 10,000 neutrons. That just isn't going to happen. So anyhow, one of the neutrons changed into a proton. So the atomic number goes up by 1. Used to have 6 protons, now you have 7 protons. It gives off a neutron, and let me make sure nobody is thinking that a neutron is a proton and an electron stuck together. That's not how it works. An electron gets made out of a different kind of particle during the decay. Electrons do not feel the strong force. There's nothing to hold it in the nucleus, so zip, out it goes. And also, there's another particle created called an antineutrino. We aren't really going to get too deeply involved in talking about elementary particles. If you're interested in it, like send me an email or grab me after class or something like that, and tell you whatever you want to know. Well, assuming I know it. I mean, I don't claim to know everything about everything. But neutrinos, not to be confused with neutrons, similar name because once again, it's electrically neutral, but neutrinos, unlike neutrons, do not feel the strong force. They have no charge, so they don't feel electromagnetism, and they have little or no mass, so they don't even feel gravity. The only way they ever interact with anything is by the weak force, and that, of course, is pretty weak. So, yeah, millions of them have passed through my body just in the few moments that I've been sitting here talking about them, because something like 3% of the energy from the sun is given off as neutrinos rather than electromagnetic radiation. But I was saying that, gamma rays are, alpha rays only go through a little bit of paper, beta rays takes a couple pieces of metal, gamma rays, a couple centimeters of lead to block them out. You want to talk about penetrating. Most of the neutrinos that hit the Earth coming from the sun pass right through the whole planet and go out the other side. These are very difficult to detect, but they are produced by beta decay along with these other things. And actually, the little bar over the top is the symbol for an antiparticle. You'd get a regular neutrino if this was a beta process where you gave off a positive electron. But when it gives off a regular negative electron, you get an antineutrino. And that's starting to get farther into elementary particles than I meant to. But that's, for a complete description of a beta decay, you have to mention that that thing is created also. And then finally, we have gamma rays. Gamma rays are electromagnetic radiation. Okay, a gamma ray is a photon. Well, like I said a minute ago, nuclei have energy levels. The protons have their energy levels, neutrons have their energy levels. And if somehow the nucleus is given a jolt of energy, it can be put into an excited state. This could happen if the nucleus collides with another nucleus, or if the nucleus has just undergone an alpha or a beta decay, it might be left in an excited state after that, and then follow up with a gamma ray. Just like with the electrons orbiting in the outer part of the atom. If you get the particle up into an excited state, the excited states are unstable, and in very little time, it's going to fall down to the lowest available energy level. So just like when a hydrogen atom gives off visible light or some other nearby frequency. However, the forces in a nucleus are much stronger, so you're dealing with much larger amounts of energy. So instead of a photon in or near the visible part of the spectrum, you're down in the gamma ray part of the spectrum, where the photons, instead of having like 2 or 4 electron volts, they have thousands of electron volts or more. So if you write out an equation for a gamma ray being produced, well, in this case, iodine 123. Unlike alpha or beta decay, it does not change the atomic number. Photons are electrically neutral. They do not carry any charge out of the atom with them. So if you had 53 units of charge before, you've still got 53 units of charge afterward. Photons are also massless, so the mass number does not change. Whatever isotope you had before is the same isotope you have afterwards. It's just dropped out of an excited state into its ground state is all. So a little practice for you. Fill in the blanks. So I'll assume you tried that yourself. Let me tell you the answers. Number 1, the number across the top stayed the same, 64 before, 64 afterward. But the number across the bottom went up by 1, which would indicate that the nucleus gave off a negative particle. Okay, well, electrons have a charge of -1, and they aren't massless, but their so-called mass number is 0 because it takes something like 2,000 of them to add up to the atomic mass, to 1 atomic mass unit. Actually, a better way, no, let's not even get into that. So that indicates that this is a beta decay, okay? Electron has a mass number of 0, it has a charge of -1, and looking at the numbers on the copper and zinc atoms there, you can see that that's what was produced. So what goes in the blank symbol for an electron is a lowercase e. Mass number of 0 on top, the charge on the bottom, plus, and it took them until the 1930s to figure this out. And neutrinos were not actually observed until the 1950s because they're so hard to catch. You have to build these great big detectors and then have detection equipment that can pick up on just 1 or 2 of them occasionally getting caught. But don't forget the anti-neutrino Greek letter nu with the little bar over the top to say it's an anti-neutrino. Then the second one. Okay, looking at the top, the mass number goes down from 190 to 186. So you're talking about a particle with a mass of 4. And then on the bottom, the charge goes down from 78 to 76. So what's leaving the nucleus is something with 2 units of charge. And so that would be a helium nucleus. Or if you're into Greek letters, you could use the Greek letter alpha instead of He for helium. I'm going to go with this. Okay, so to answer these types of questions, you have to know what an alpha particle is. You have to know what a beta particle is. And you have to know what a gamma ray is. And you have to know that the numbers are supposed to add up on both sides. You're supposed to, the equation should balance. Last one. The 123 didn't change. The 52 didn't change. So we're looking at a massless, chargeless particle. That would be gamma ray, represented by the Greek letter gamma. And if you're going to fill in numbers next to that, it would just be a bunch of zeros. Half-life. Some substances decay faster than others. Uranium-238 has a half-life of about 4.5 billion years. That's the reason it still exists in the environment, is the age of the Earth happens to be about 4.5 billion years. So there hasn't been enough time for it to go away. Our understanding of the formation of the solar system indicates that there was probably a supernova someplace nearby shortly before the solar system formed. And all kinds of isotopes can be created during a supernova. So that injected this stuff into the nebula that our solar system formed out of. And since then, uranium has such a long half-life, there hasn't been time for it to go away. At the other extreme, some of the isotopes that are created in nuclear reactors have half-lives that are in the million, or particle accelerators, or another way to do it, half-lives in the millionths or billionths of seconds, or even shorter, and everything in between. Carbon-14 is a few thousand years. Tritium, as I might have mentioned, has a half-life that's around 15 years, 14, 15, 13, something like that. So what the half-life means is the time for half of the stuff to go away. If you had, well, let's say 5,700 years ago, some remote ancestor of yours had a gram of carbon-14. I don't know where somebody would have gotten it 5,700 years ago. Separating isotopes from each other is not exactly something you can do sitting around the campfire after the hunt, but just for the sake of argument. Today, if your ancestor has passed this lump of, I mean, it's just a stupid piece of coal. I don't know how it would get to be a family heirloom, but if it's been passed on down to you after all these years, you will now have half a gram of carbon-14, because the daughter nucleus, when it decays, is a gas. Carbon-14 decays into nitrogen-14, which would kind of wander off and be gone. So the way it works then is some remote descendant of yours, 5,700 years from now, well, a naive person might think that if half of it goes away in 5,700 years, after another 5,700 years, there won't be any of it left, but it's not a linear graph. It's an exponential decay, okay? So half of what you have will be left after 5,700 years, just like you got half of what there was 5,700 years ago. And whoever your remote descendant is will pass down to their remote descendant half of what they started with. So, you know, 1/2, 1/4, 1/8, 1/16, every 5,700 years, it gets halved again. To make that into a formula, N is the number of nuclei present. How many carbon-14 atoms are there in this little lump of coal you've got? And 0, or if think of it as NO if you want to, O for original, that's how many nuclei there were at T = 0. 0.5 to the T, T 1/2 is the half-life. Okay, the 1/2 is just a little subscript, a label. T 1/2 is the half-life. That would be the 5,700 years if you're talking about carbon-14. So T is how far are you down the lowercase t? How far down the time axis are you? What time is it? And if you plot up that exponential function, it looks like this graph that I've drawn here. R stands for the, well, R for rate, R for decay rate, also called the activity of the sample. If it's carbon-14, that's how many beta particles per second go shooting out of the thing. Well, that's going to be proportional to the number of nuclei that's present. If you've got 1/2 gram of carbon-14, but your friend has a whole gram of carbon-14, there's going to be twice as many beta particles every second coming out of your friend's chunk, because that gram could be thought of as 2 1/2 grams, and each 1/2 gram is going to give off as much as your piece does. So twice as much carbon-14, you're going to get twice as much activity, twice as many beta particles shooting out of it every second. So the decay rate, the activity, tapers off according to the same exponential function that the number of nuclei does. The SI unit for the activity is called the becquerel, which is a really low level. I mean, your body is more radioactive than this. I mean, your body contains a small amount of carbon-14 and traces of a few other radioactive substances, even if you haven't been going into parts of a nuclear power plant that you shouldn't have been into. Your body is more radioactive than this, but that's the unit that'll fit well with other units around it when you do some kind of a calculation. A more let's say an also popular unit, because it's quite a bit bigger, is a curie. Kind of a random looking number, 3.7 times 10 to the 10th. I believe it was originally chosen because that's approximately the activity of a gram of radium, which seemed like a good idea at the time. Quite often you'll see things, the activity of something rated in millicuries or microcuries. Something, a curie is, you know, if a becquerel is practically nothing, a curie is hot. You do not want to walk around with something in your pocket that has an activity of 1 curie. That would not be smart at all. So what I did on the top of the next page is, what if somebody gave you a problem involving this function here, but asked you, well, how much time does it take to get from this to that? You would have to solve this function for t. And the way you would do that is you would first divide both sides by R0, and then you'd have to take the log of both sides and do some more algebra. And the prerequisite for this course is such that you should be able to do that. But yeah, maybe you're a little on the rusty side. So I did it for you. This equation on the top of the next page is basically the same equation. It's just after several steps of algebra, excuse me, solving it out for t, the equation looks like that. And so both versions are written on your formula sheet, and you just grab the version that's appropriate to the question that you're being asked. Well, speaking of questions, there are 3 of them there. That'll keep you busy for a little while. Do one, pause it, do one, start the video up, watch me go over that one, pause it, do the next one, or something like that. But I'll start running through them now. Number 3, its activity today is 10,000 or 1,000 decays per second. What will its activity be after 10 years? Well, there's 2 ways you could do this. There's the somewhat more sophisticated way. Well, one way is there's that formula that what will its activity be 10 years from now? It's asking for R, the decay rate. So you could fill all the numbers into R equals R0 times 0.5 to the, all of that stuff, and punch it up on your calculator, and that'll work. Or, because this happens to be an even number of half-lives, okay, the half-life is 5 years. The amount of time it asks about is 10 years. That's exactly 2 half-lives. So because it's an even number of half-lives, all you actually have to do to get the answer, this seems like the more straightforward way to me, is just simply to say, if you've got 10,000 decays per second now, then, or why do I keep saying 10,000? It's like I got to go back to kindergarten and learn my numbers. You got 1,000 today. After a half-life, that'll be cut in half. So 5 years gets you from there to there. Another 5 years gets you from there to there. So after 10 years, it'll be down to 250. The answer is 250. Or, as I said, your alternative is R equals R0 times 0.5 to the T over the half-life. The original rate is the 1,000 decays per second. The half-life is 5 years. T, the amount of time that's passed, is the 10 years. You pull that, if you punch that up, you should get the same answer. So that's number 3. Might want to pause it here and work on number 4. And now that you're back, I should probably look at it and see what number 4 says. Oh yeah, radioactive dating. I should tell you the story that goes along with that. How does this work? I mean, this is a significant application of radioactivity. Long time ago, if you were like an archaeologist or a paleontologist or somebody like that, it was really hard to figure out how old stuff was unless it was some ancient document from Egypt that had a date written on it or something like that. But once you get well into the 20th century and radioactivity and other related topics came to be well understood, you could date things if they contain carbon by this carbon dating process. The story begins with cosmic rays, actually. The Earth is continuously bombarded by high energy particles from deep space. There's lower energy stuff that comes from the sun, but the really, really high energy stuff comes from deep space, someplace way outside the solar system. And so it's high energy charged particles, broken up bits and pieces of atoms, a lot of protons, some heavier ions. And these come screaming in toward the Earth at extremely high energies. The first thing they encounter is the Earth's atmosphere, of course. So you've got some nitrogen. The Earth's atmosphere is more than 3/4 nitrogen. You've got some nitrogen molecule just kind of floating around, taking it easy, not bothering anybody up in the upper atmosphere. And all of a sudden, this cosmic ray just smacks right into it. And the energy of the collision is enough to cause, well, what amounts to basically the reverse of a beta decay. It can transform the nitrogen-14 into a carbon-14 atom. So there is a certain equilibrium concentration of carbon-14 in the atmosphere. Most of the carbon in the atmosphere is in carbon dioxide molecules, smaller amounts in other carbon-bearing molecules like methane. But as I said, there's a certain equilibrium amount, because if you go back to the equation, the decay rate is well, I guess it wasn't exactly an equation. It was written on the bottom of the previous page. The decay rate is proportional to how much of the stuff is there to decay. So if the atmosphere contained more than this equilibrium concentration of carbon-14, it would decay away faster than more is being produced. If it contained less than this certain concentration, which I think is like about 1 out of every trillion carbon atoms or something like that, if I remember right, don't quote me. Maybe it says in the question. Not really. But if it had less than this equilibrium concentration, it would be decaying away less rapidly than more is being made. So there's a certain, when you have a certain amount of carbon-14 present, the rate that more is being made exactly equals the rate that it's decaying back into nitrogen-14. And so year after year, there's the same amount of, at least approximately, the same amount of carbon-14 in the atmosphere. Plants get their carbon from the atmosphere. You plant a little oak tree, you come back 100 years, or a little acorn, you come back 100 years later, there's this great big oak tree. Where did all that come from? Well, the carbon in it anyhow, which is one of the main constituents in wood, it came from the atmosphere. You know, you ever took biology, they probably taught you about photosynthesis and all that. The plant takes in carbon and well, we don't need to go off in a long story about that. But all living things either get their carbon from the atmosphere or eat other living things that recently got their carbon from the atmosphere. So all living things have in them this same ratio of carbon-14 to carbon-12 that you find in the air until they die. And then they stop taking in carbon from the atmosphere. And as the years go by, since carbon-14 decays away into something else, as time passes, there's less and less carbon-14 left. And the carbon-14 to carbon-12 ratio gets smaller and smaller and smaller. So you can tell how old something is by how much carbon is left in it. Now, I did slip in the word approximately at one point when I talked about how much carbon's in the, you can get fluctuations in how much carbon is in the atmosphere from, you know, there can be a surge in radiation from solar flares and different stuff like that can happen. But there are corrections they can make for that. They've been doing this long enough now that they've done a lot of studies where they look at things that can be dated in other ways. You can go back 2,000 or 3,000 years with tree rings. You can go back further with layers of sediment that you find in lakes. They can, annual, seasonal layers of sediment where you can count the years off and you extract a little sample from there. You know how old it is from counting the layers or counting the tree rings or whatever, and see how much carbon-14 is in there. And so you can correct for any variations in how much carbon might have been in the atmosphere because of complicating factors. But carbon dating can't be used for things that are more than, I don't see the half-life's only a little over 5,000 years. So you get up around 40 or 50,000 years, there's too little of the stuff left to measure. But other radioactive isotopes with longer half-lives can be used to date older things. Geologists use a variation of the same idea to date rocks that are millions of years old, hundreds of millions of years old. And they just use isotopes of other elements that have much longer half-lives and do a similar type of process. So anyhow, that's the story of carbon dating. In this particular example, we have a 100-gram piece of charcoal with an activity of 17 becquerels. Something that's alive, if it was 100 grams, would have an activity of 25 becquerels. It says 0.25 for each gram. So if you have 100 grams, the activity would be 25. Based on that, how old is it? Well, the question's asking for time. How much time has passed since this thing was alive? You've got yourself, I don't know, a mastodon bone or something like that, or a piece of charcoal out of some campfire that people made thousands of years ago, and you want to know how long ago it was they were living there. So it's asking for time. That would be the version right at the top of this page here where it's solved out for T, where it looks like this. T equals T1/2, the half-life. Ln is the natural log. They should have covered this in some math class that you've taken, but if they haven't, well, it's a button on your calculator. Push it. Fill in the numbers and we'll have the answer. Half-life, 5,730 years. Half-life of carbon-14. Ready for the parentheses yet. Ln stands for natural log, log to the base e, as opposed to a common log, which is log to the base 10. R0 is the original decay rate back when the mastodon bone was alive. R is the rate that we have now after the time t has passed. So I guess another way to put it is R0 is always going to be the bigger one. So we've got 17 over 25, not 25 over 17. If you had any trouble punching that up, this is what should have happened. If you recopy the 5730, the natural log of 17 divided by 25, that should have come out negative 0.3857. And the natural log of 0.5, that's part of the formula. That'll always be the same thing under there, 0.6931. And so you multiply, the minus signs cancel, of course. You multiply that, you divide by that, and it comes out rounding off just 3188, but I rounded off to 3 significant figures. This kind of thing usually has a plus or minus range of like 40 or 50 years anyhow. So I'm stretching it, you know, taking it right down to the nearest year would be kind of an abuse of significant figures. 3190 or so. And so I guess I shouldn't have been calling it a mastodon bone because mastodons have been extinct for longer than that. Mastodon bone would have to be at least like 10,000 years, something in that 10, 12, something like that. At least 8 or 9. I don't know, you have to talk to the biologists if you really care about that one. Okay, so here's where you should do the number 5. And now that you're back after pausing it, radioactive tracers, another application of radioactivity. The idea here is you want to trace where something goes by mixing a radioactive substance with it. And then you can see where the stuff goes by where the radiation is coming from. There are both medical and industrial applications for this type of thing, but in this case, it's a medical application. You've got a doctor who wants to check out your thyroid gland, I'd say. So this particular isotope of iodine, it works out pretty nice because it has such a short half-life. Having somebody ingest a radioactive substance is a good way to kill them if it's got a really long half-life. This was a problem in the early 20th century, actually. Shortly after radium was discovered, somebody got the idea it was good for you. I guess they noticed that it shrunk tumors or something like that. So they kind of extrapolated from that to all sorts of other benefits that it didn't actually have. And you could go in the drugstore and you buy a bottle of tonic. It was full of radium and you drink it. And yeah, this is where the Food and Drug Administration came from, among other problems that existed at one time. People sometimes talk about government regulation as if it's a good, or as if it's a bad thing. Well, too much of it can be a bad thing, but you don't want people to be able to go selling you patent medicines with radium in it, because radium is in the same column of the periodic table that calcium is, which means it has similar chemical properties, which means your body, after you drink it, goes, oh yeah, I think that's calcium. We'll put that in the bones. And that does not end well at all. That's a very slow, unpleasant way to die, and there's nothing anybody can do about it. So anyhow, something with a long half-life is not a good thing to ingest. But this radioactive isotope of iodine has a half-life of only 13 hours. And even aside from that, you're going to pee most of it out before it has a chance to decay anyhow. But all isotopes of iodine would have the same chemical properties. So it's going to be taken up by your thyroid gland the same way that regular stable iodine is. And the doctors can monitor the rate that the gamma rays coming from your thyroid, you know, does the radiation build up at the rate that it's supposed to coming from your thyroid gland? It's basically like getting an X-ray, only the source of the X-rays is inside your body instead of you being shot with them from the outside. So anyhow, that's what's going on in number 5. Dose has an initial activity of 300 microcuries. How much of it's left 2 days later? How much is left? That's asking, or no, it isn't asking for how. It's what is the activity of it 2 days later? It's asking for R. So I should move the camera over to the other part of the blackboard. Sort of like that ought to work. Number 5, it's asking for R, the decay rate, the activity. So you want the version that's solved for R as opposed to the version that was solved for the time. R equals R original 0.5 to the time over the half-life. Fill in the numbers. Originally, when they first put the stuff into you, it had 300 microcuries, is the activity. 0.5 to the, okay, if the half-life is given in hours, then the time t has to be, it doesn't matter what unit you use. You can have them both in fortnights if you want to, if you have any idea what a fortnight is in the first place, but they have to be the same. So since the half-life was given in hours, I'm going to change the 2 days into hours in order to match it. So 48 hours over 13.2 hours. So what we have here is 0.5 to the 3.636 power. And yeah, I guess you can read that all right. 0.0804. That's what this factor on the right is equal to. And then you multiply the 0.0804 times 300. And that comes out 24.1 microcuries. Whatever unit is on R0 is the unit that you'll have on R, because the exponential factor is dimensionless. It has no units. Next thing down the page, reaction energy, disintegration energy. This is the same sort of thing as the binding energy that I talked about earlier. Just the only difference is previously I was talking about a spontaneous radioactive decay. Let's see. That looks pretty good right around there, I guess. It's a little crooked on the top, but maybe that looks better. Previously, I was talking about a spontaneous radioactive decay where you're just sitting around drumming your fingers and watching a piece of, radium or whatever it is. And then all of a sudden, it decides to, at some random moment, spit out an alpha particle or a beta particle or something. Well, you don't have to be that passive. You can shoot something at the nucleus and cause a reaction instead of just watching spontaneous decays. So, like it says up here, shooting something like a neutron, for example, at a nucleus can transmute it into another element. So some neutron or some alpha particle or some other ion, whatever it is you're shooting at the nucleus, you've got this original nucleus X and the thing you shot at it. After the reaction, you've got some other nucleus, Y, that's been created, plus who knows what else. If this was like an alpha decay, then there would be no A. You'd just have the parent nucleus and then the daughter nucleus in an alpha particle, but lots of other possibilities here. Back in the Middle Ages, alchemists tried to turn lead into gold. And yeah, nice try, guys. Never occurred to them that if they could make all that lead into gold, gold would become worthless anyhow. So what would be the point? But I guess the idea was that they would just turn a little bit of lead into gold and not tell anybody else how they did it so that gold was still valuable. Anyhow, today with nuclear reactors, we actually can convert one element into another. Making gold in a nuclear reactor, well, the thing is, it's still cheaper to just dig it out of the ground. But there are a lot of other substances you can make in a nuclear reactor that don't exist naturally, that have useful properties for industrial purposes or for medical purposes or for blowing up people you don't like in large numbers. And so anyhow, all of those, this is supposed to be some generic reaction that would cover all of those types of things. The disintegration energy would mean, a disintegration would be a radioactive decay. Like I was saying, if it was an alpha decay, there would be no A, there would just be the X. Reaction would be like if you shot something at it. Either way, the energy liberated is the same basic idea as the binding energy I talked about earlier. You've got, add up all the mass that's on the before side of the arrow, add up all the mass that's on the after side of the arrow. The difference between those times c squared, because E equals mc squared, would be the amount of energy given off by the reaction. Or if the reaction actually absorbs energy, you'd get a negative number. So, for example, I want you to calculate, they call it the Q value because that rolls off the tongue easier than saying reaction energy, I guess, I don't know. But the amount of energy given off by the alpha decay of radium-226. And it tells you here, see, on the one side of the arrow, you would have just the radium nucleus sitting there. On the after side, you would have this radon nucleus and, no, I'm sorry, this radon nucleus together with this alpha particle. You add these two together and it's just a little bit less than the radium was. And that's, they call it the mass defect, the little bit of difference there is in the mass. That's equivalent to this much energy. So see if you can get this number. And if you need to hear me explain it. I guess it looks best about that. Let's see. This is number 6. Okay, the total mass before. Add up all the masses on the left-hand side of the arrow, and in this case, there's only one thing on the left-hand side of the arrow, which is our radium nucleus 226.025,406 in atomic mass units, minus the total mass that you have on the after side of the arrow. That would be the 222 point. This gets a little tedious after a while, doesn't it? Nothing to be done about it, though. 0.17574, and the alpha particle is 4.002603. Got that. I didn't leave myself any space to write the 931.5, so I'll just kind of make a spot for it. Yes, all of that's in the field of view of the camera. So the radon nucleus plus the alpha particle, the total amount of mass that you have after the event is 226.020.177. See, just a little bit lighter than what you had before. And the missing mass is the energy that was given off when, in this case, it would be the kinetic energy of the alpha particle as it goes zipping away. There aren't any neutrinos given off or anything like that. It would just be the alpha particle. So the alpha particle's kinetic energy. When you subtract that minus that in atomic mass units, the missing mass is that much. 931.5 makes it 4.87 mega electron volts. Millions of electron volts. Nuclear. Oh, yeah. I suppose I should point that out. Underneath the question there, it points out that if the Q value is positive, the process can happen spontaneously. In this case, positive 4.87. So yeah, radium really can spontaneously decay into radon by giving off an alpha particle. On the other hand, if the Q value is negative, that's what the chemists would call an endothermic. Yeah, exoendo. That would be an endothermic process. It's been a while since I took chemistry. I had to stop and think for a moment. That's not going to happen spontaneously. It's only going to happen if somebody comes along and provides the energy. You get the same sort of thing with chemical reactions. There's really a lot of similarities between chemical reactions and nuclear reactions. It's just with chemical reactions, you're dealing with the electromagnetic force between atoms. Here you're talking about the strong force, and instead of combining atoms in different ways, you're combining nucleons in different ways, but a lot of the same principles apply. One of them is that something can happen spontaneously when it gives off energy, but not the other way around. If all it takes is one tiny little spark, and if things are really dry, it starts a grass fire and the whole field can go up in flames spontaneously, more or less. And that's, a process that gives off energy, so that's allowed to happen. On the other hand, you don't find carbon dioxide, because, when something burns, the carbon in it, if it's a grass fire, the carbon in the grass gets made into carbon dioxide that goes up into the atmosphere. You don't find the reverse process happening spontaneously. You don't find carbon dioxide splitting itself into carbon and oxygen, and you go outside in the morning and find soot all over your car because that was you have to supply energy, like the sunlight hitting a leaf when there's photosynthesis. You have to supply energy to break up a carbon dioxide molecule. And so that does not happen spontaneously. And this is the same sort of thing, just talking about nuclear reactions instead of chemical ones. Let's see, two general types of nuclear reactions, fission and fusion. Fission, like it says in front of you, is when you take typically a fairly heavy nucleus and you split it into smaller ones. Fusion is when you take typically some small nuclei and stick them together to make a bigger one. Examples: the original atomic bombs used at the end of World War II made use of fission. Uranium or plutonium being broken into smaller nuclei and giving off energy in the process. Any sort of peaceful nuclear reactor, or even semi-peaceful, whether you're talking about generating electricity or whether you're talking about providing the power for a nuclear submarine, which I don't suppose quite qualifies as entirely peaceful, but those are all fission reactors. They all run on uranium. Fusion, well, there's the hydrogen bomb that was developed in the early 1950s and has never actually been used in a real war, fortunately, because they're nasty things. That's primarily a fusion reaction that's going on there. And also the sun. The sun is basically an enormous hydrogen bomb. The reason it doesn't blow up is gravitational attraction. You've got two opposing tendencies there. On the one hand, you've got a lot of outward pressure trying to make it blow up like a hydrogen bomb. On the other hand, every atom attracts every other atom gravitationally, which makes the sun want to collapse. And the sun is in sort of an equilibrium state between those two opposing tendencies. Details about fission and fusion on the next page, which, by the way, will be the last page of new material in this entire course. So bring it down where you can see it. Typical example of a fission reaction. The fission of uranium-235. If you dig uranium ore out of the ground, more than 99% of it is uranium-238, which is not nearly as fissionable. One of the important parts of any nuclear weapons program is to extract the uranium-235, which is like 0.7% of the natural ore. That's what the gas centrifuges are for, whenever you hear about them on the news, like if they're talking about Iran or something like that. So anyhow, this is the isotope of uranium that splits real nice. If you're going to split something, you have to split it with something. If you go out back to split some wood, it'll work better if you have an axe. If you just sit there in a folding chair looking at the wood, well, you'll have a nice relaxing afternoon maybe, but you aren't going to have any fuel come winter. So in the case of uranium, what you split it with is a neutron, okay? You shoot a neutron at the uranium nucleus, and I kind of skipped over the intermediate step. The neutron very briefly bonds to the uranium nucleus, forming a uranium-236 nucleus, but it's left in a state where it's undergoing violent oscillations, and the uranium-236 doesn't really exist long enough to be worth talking about. It breaks apart. There are many possibilities for what the fragments might be. This is just one of something like 90 different combinations of nuclei that might come flying out when this thing gets split. As before, the numbers across the top have to add up to the same thing on both sides, and the numbers on the bottom have to add up to the same thing on both sides. So if I gave you any sort of a question where you have to fill in the blanks, that's how you would figure it out. You might remember a while ago, I mentioned that the farther down the periodic table you go, the more extra neutrons there are in a nucleus. Right up in the upper, the first few elements, carbon 12, six protons, 6 neutrons. You get down around iron and there's, a couple extra neutrons. You get all the way down into the really heavy stuff at the bottom of the table, and there's a number of extra neutrons, which means that if you take something from the bottom of the periodic table, like uranium, and you split it into some lighter nuclei from around the middle of the periodic table, there's going to be neutrons left over. There aren't as many extra neutrons in these lighter substances. In this case, there are 3. You can figure out that there's 3 neutrons produced by the fact that, you had 236 units of mass, 235 plus 1, before the event. 141 plus 92 is only 233, 236 before, 233 afterward, must be 3 neutrons were left over. Thing is, it was a neutron that split the atom in the first place. So, well, I'm getting a little ahead of myself. Down here is where it says about a chain reaction, but as long as I've started on the story, if you've got enough other enough other uranium nuclei around for these neutrons to hit, they'll split them, releasing even more neutrons, which will hit even more atoms. Years ago, somebody made a great educational video that I haven't seen the original for years and years and years. Maybe I wouldn't even recognize it if I saw it. But there are several imitations on YouTube that would be very easy for you to find if you just put something in the search box to look at it. What somebody did, some 1950s Your Friend the Atom type film, I think. But to illustrate the idea of a chain reaction, they got a room, they took all the furniture out of it, and they must have bought every mousetrap within a 200-mile radius. They had the whole floor of the room just covered with mousetraps. And they must have spent a couple of days setting it up because all the mousetraps were pulled back and ready to go. And each one had 2 ping pong balls sitting on it. So when they finally got it all ready, they started the cameras going, and this guy leans in the door with a ping pong ball in his hand, and he tosses it into the middle of the room, and it lands on a mousetrap. And of course, that springs the mousetrap. So as the thing flips up like that, it throws the 2 ping pong balls into the air that were sitting on the mousetrap, and they each land on other mousetraps, which means now, it flips both of them. You've got 4 ping pong balls in the air, and then 8, and then 16, and then 32. And in a matter of a few seconds, the whole room just explodes with ping pong balls. Well, that's an out-of-control chain reaction. The mousetraps are supposed to be atoms, and the ping pong balls stand for neutrons, okay? So this neutron comes along, lands on the mousetrap. In this case, 3 ping pong balls get thrown out by the mousetrap, and they go on to split other atoms and so on and so on. So aside from there's what's called a critical mass. And I guess I didn't actually put this in the notes, so this is just a little footnote that isn't officially part of the course, but if you have too small of a piece of fissionable material, uranium-235 perhaps, then too many neutrons escape before they hit anything. All the atoms are too close to the surface. It would be like having just a little circle of a little circle of mousetraps a few feet across. You throw the ping pong ball in there, and the 2 ping pong balls go up, but one lands outside the circle where there's no mousetraps. The other one comes down on a mousetrap, and it throws up the 2 ping pong balls, and they both land outside, and the chain reaction dies out. So if you have too small of a piece of fissionable material, less than the critical mass, chain reaction dies out. Uranium has a long half-life. Uranium-235, the half-life is a few 100 million years. So it's not that radioactive. I mean, you know, I wouldn't sleep with a piece of it under my pillow, but it's not that dangerous compared to some radioactive substances anyhow. But the critical mass, if I remember right, is somewhere around 50, 55 kilograms. Don't quote me on that, look it up. I mean, if you want to build an atomic bomb, detailed instructions are available on the internet these days. So if you want to look up the critical mass, you can find it in about 20 seconds. But I think if I remember right, it's around 50 kilograms, give or take. So what you do is you get two pieces that are smaller than the critical mass, maybe 30 kilograms here and 30 kilograms there. And you put an explosive charge, some TNT behind this one. And at the moment that you want to wreak death and destruction, you just set off that little charge so that it violently shoves the one piece of uranium into the other piece of uranium so that they effectively merge into a single piece of uranium, which is now more than the critical mass. And so the chain reaction then runs away in the way I was just describing, and you vaporize a medium-sized city. There are other designs that are more sophisticated. What I just described is the gun type of bomb that was dropped on Hiroshima. The one they dropped on Nagasaki was a plutonium bomb that was somewhat more sophisticated. But anyhow, atomic bombs are actually frighteningly easy to make. I mean, stop and think about it. Compare the technology of the 1940s to what we have today. These people were listening to vacuum tube radios and riding around in trains pulled by steam locomotives. And that technology got the atomic bomb. So the thing that keeps everybody from having one in their garage so they feel safe from their neighbors today is that it's hard to get your hands on the materials. I mean, it takes a certain amount of expertise it's not, you know, it's not quite as simple as putting together some furniture from IKEA, but the biggest obstacle is just getting your hands on weapons grade uranium or weapons grade plutonium. Anyway, back to the script here. Work on number 7. Write the equations. And if this was on a test, of course, it's all about getting all the numbers right on the top and the bottom on each part of the equation. I guess I better erase a spot to do this. Okay. My explanation of the answer to number 7. So it says, part A, uranium-235 splitting. What some people do who really have no idea what they're doing, and so they don't really get much credit if this is all they write on the test, they look at that and go, oh, uranium-235 splitting into those two things. Okay, 235, 92, U for uranium, goes to, and you don't have to know these chemical symbols. This isn't a chemistry class. 140 on the top, 54 on the bottom. Xe, I believe, is xenon. So they just write that and hope for the best. But alas, the best is not what occurs. First problem, there's a couple of problems here. One is the numbers don't work out. 140 plus 94 adds up to 234, not 235. And so there's a problem there with the masses don't balance out the way they're supposed to. But aside from that, also, a uranium atom, you know, like I was saying before, it's like splitting wood. The uranium atom doesn't just split itself. You got to hit it with something. And the thing you hit it with is a neutron. 1 unit of mass, 0 units of charge. That's why they call it a neutron. So my misguided student I was talking about, my hypothetical misguided student, left out the neutron. That's one mistake. The other mistake is left out some more neutrons over here. Maybe he's just some sort of an anti-neutron person. But we have to make the mass balance out. With this, now we've got 236 units of mass to the left of the arrow. Since this only adds up to 234, that tells you it's 2 neutrons that need to be included over here. And that's the correct answer for that one. Part B. If it's uranium being split, it's always going to be the same thing to the left of the arrow, okay? No matter, you know, uranium splitting into this plus that, whatever this plus that is, it always starts out the same. You've got a neutron, or for that matter, if it's plutonium that you're splitting, you're still going to hit it with a neutron. So it starts out the same way that part A did. And this time we're splitting it into one of those. I believe SN is tin, if I remember my chemistry correctly. And molybdenum, I think, if I pronounced that correctly. Well, there's going to be neutrons. We got to figure out how many. 132 plus 101, that adds up to 233. That plus that is 233. 235 plus 1 adds up to 236. So we still haven't accounted for 3 units of mass. That would mean that this particular reaction produces 3 neutrons. A few words about fusion. I think I ought to lift this up some. Come on, sharpen up. Maybe a slightly different distance. This camera's getting ornery. Focus. Okay, got it. inside the core of the sun, right down in the middle, it's very hot and it's very dense. Now, protons don't generally like each other very much because they have the same kind of charge and so they repel each other. But if you go packing them really close together, because it's so dense in there, and if they're moving really fast, because it's millions of degrees down there, over 10 million degrees actually, then protons will sometimes, if they approach each other just right, and if they approach each other fast enough, instead of being turned away by Coulomb's law of repulsion, sometimes they'll go right up so they touch. If they touch, the strong force kicks in and they bond together. So some proton encounters another proton and they stick together. Well, that's going to be unstable against beta decay. Actually, reverse beta decay, where it gives off a positron instead of an electron, gives off a positive electron. So then you have a nucleus that's a proton and a neutron stuck together, heavy hydrogen. Well, then one day that bumps into another proton. And if it actually touches, the strong force kicks in. And anyhow, through a series of a few collisions like that, what eventually happens is that what started out being 4 protons ends up being a little lump of 2 protons and 2 neutrons, which would be a nucleus of helium-4. The other miscellaneous particles carry away the other 2 units of charge, a couple of positrons, and a couple of neutrinos are also given off, and a significant amount of energy is given off in the process. And that's what keeps us all from freezing to death, because deep space is pretty cold. So that kind of makes a long story short. But to get it to work requires, like I was saying, really high temperatures and a lot of pressure. So if you wanted to try and harness this process here on Earth, well, actually, because you don't have the really high pressure and density helping you out that exists in the center of the sun, you have to compensate for that with an even higher temperature. You need something like 100 million degrees Celsius to get this reaction to take place on Earth. So how are you going to get something that hot? I know, set off an atomic bomb. That's the idea behind a hydrogen bomb, is you get your heavy hydrogen in there, your deuterium and your tritium, and you get them up to 100 million degrees roughly by setting off a fission device, and that creates the necessary conditions for fusion to take place so that you get an even bigger bang than you would from just the fission reaction alone, okay? So the reason that you get all the radioactive fallout when somebody sets off an atomic bomb, fusion is actually a fairly clean process. I mean, it produces some tritium and things like that, but the half-lives are short and you wait a few years. And the main problem, though, is the fission device that sets off the fusion reaction. That's what creates all the nasty stuff that then blows around and poisons everybody. And so anyhow, it would be really nice to harness this process for some peaceful purpose rather than just blowing things up. The problem is that such extreme conditions are needed that you can't just build some vessel for it to take place in like you do with other types of power plants. You want to burn some coal? Well, you just do it you put up a building made out of concrete and steel and things like that, and you burn your coal in there. Or if you're going to have a fission power plant. Well, at least when it's operating properly, the reactor doesn't get any hotter in there than when you're burning coal. And there again, you just build a structure out of concrete and steel and things like that to contain the reaction. You want to be careful that nothing gets out, because radioactive stuff, you need to be a little more careful than when you're burning coal or natural gas or something. But fusion, on the other hand, 100 million degrees, that's going to vaporize any kind of a structure you try to put it in. So how are you going to contain your reaction and keep this hydrogen from just drifting away and your fire goes out because everything drifts apart? Well, there's a couple of approaches to that they've been working on. One, for example, is to try and contain it with a magnetic field. They've been working on this since the 1950s. And yeah, they're still working on it. Part of the motivation is just that fission or fusion research is closely related to weapons research. And of course, there's always money from the guys with the guns. But the other motivation is that you would effectively have limitless energy. There is enough heavy hydrogen that could be extracted from seawater to meet our energy needs, at least at present rates of consumption, for something like the next 1,000,000 years. I mean, there is some debate about how many centuries until fossil fuels run out. World reserves of uranium aren't really going to last an awful lot longer than that either. You start talking fusion, there's enough fuel for 1,000,000 years just burning heavy hydrogen. And then we can start talking about how much lithium is in the world, because you can make tritium out of lithium. And then, you would think after a few million years, we'd find some way to bring hydrogen from Jupiter or someplace like that. And yeah, we'd be all set. No more importing fuels from unstable parts of the world, and no more greenhouse gases, because, I mean, we need to wean ourselves off fossil fuels just because of the whole geopolitical situation. But aside from that, don't let anybody tell you to the contrary. We are cooking the planet. In the 19th century, people used to sail up into the Arctic looking for the Northwest Passage, and their boat would get caught, locked in the ice, and they'd sit there for months and months and finally decide to try and abandon ship and head south. And a few native people saw them walking along and met them briefly, and they never did make it back. They all died. Yeah, that was the 19th century. It's been, I think 3 or 4 years ago at least, maybe 5, was the first time a cruise ship went through the Northwest Passage with, a buffet and like roulette tables and things like that. And because the ice melts back by late summer, the ice is melted back so much that it's becoming a military thing. It's the Arctic didn't used to be navigable, but as it becomes navigable, it's like, okay, who's going to control it? We have an Arctic coast. The Russians have an Arctic coast. There's the Sweden and Iceland, and then of course there's Santa Claus. The projections now are that by 2050 there's going to be open water at the North Pole in late summer. So Santa Claus is either going to have to get a boat or move someplace where he's got land underneath him, like maybe Finland or Sweden, or he could go to the South Pole. There's land there. But so anyhow, lots of reasons to try and get nuclear fusion to work. It would produce a lot less radioactive waste than a fission reactor. And what radioactivity, like I said a few minutes ago, what radioactivity is produced is short-lived isotopes that it's not nearly as much of a problem to dispose of. And, you know, no one's gonna, anyhow. The problem is just getting one of the darn things to work. As some clever person once said, fusion is the energy source of the future. It always has been, it always will be. When I was going to college in the 1970s, people were saying, yeah, the first fusion power plants should be coming online about 20 or 30 years from now. And I'll sit here today and I'll say, okay, the state of things now is that I'm hearing we might be getting the first fusion power plants 20 or 30 years from now. And it wouldn't surprise me one bit that if one of you becomes a physics teacher, someday in the distant future, toward the end of your career, you might be saying to a bunch of students, yeah, the first fusion power plants should be coming online 20 or 30 years from now. So we'll see. But it's containing that plasma, that ionized gas, that's the issue. And there's the biggest problem with nuclear fusion is that they haven't invented it yet. And I could have probably saved quite a bit of time if I had just said that in the first place. Anyway, the last thing is a little bit about the biological effects of radiation. Why is it that being irradiated is bad for you? Why should you try to avoid it? Well, as it says there, ionizing radiation, what I mean by ionizing radiation is something that can kick an electron out of an atom or a molecule, ionize it. It's not, by radiation, I don't necessarily mean electromagnetic radiation. I could be talking about X-rays or gamma rays, but I could be talking about beta rays or neutrons or, you know, any little particles like that, that if they're shot into your body, will bust up some molecules into electrically charged pieces. If there are some of these electrically charged, busted up molecules in one of the cells in your body, it will go marauding around, wreaking havoc. And if the cell isn't able to repair the damage, then what your body does is it gets rid of that cell. But if damage accumulates more quickly than the body is able to deal with it, because you see, there's a natural background of radiation, okay? You are constantly being exposed to, first of all, cosmic rays. Some of them make it to sea level. And then there are traces of radioactive materials, uranium and thorium, in everything around you. You know, rocks, dirt, those cinder blocks that they made the walls out of. There's a little bit of that stuff in there. And so you are designed to function in very low levels of radiation. Repair mechanisms exist. But if you are exposed to significantly higher levels than that, then the damage accumulates faster than your body can fix it. And you get what's called radiation sickness. I like to compare radiation sickness to a sunburn, okay? If you go to the beach and you're laying there on the blanket with just a bathing suit on, and it's so nice and warm and comfortable, and you fall asleep. And when you wake up, it's much later than you intended, you know, and oh, does it hurt the next day? Well, ultraviolet radiation is not particularly penetrating. It only goes skin deep. And so it only damages your skin, okay? Your skin gets red and it peels. And if it's a really bad sunburn, you might even feel kind of sick because of it. A few weeks go by and you heal up and you're better. Radiation sickness from something like gamma rays or beta particles or something like that, well, they're more penetrating. They go, you know, gamma rays especially, they go right through you and out the other side. They can damage cells in any part of your body, especially not just the skin, like ultraviolet does. And so you get damage all the way through your body, and your hair falls out and you throw up. And if it's a really heavy dose of radiation, it can kill you. But if it's not so much radiation that it kills you, after a couple of weeks, just like with the sunburn, you get better. And anyhow, that's radiation sickness. Cancer. Well, what if the molecules that are damaged by the radiation aren't just any old random molecule that's floating around in a cell somewhere? What if it's the genetic material down in the middle of the cell? Then you can mess up the instructions for how the cell is supposed to reproduce, which means it may start dividing over and over again, out of control. So from either a single cell or a small group of cells, this whole tumor grows. And then some of them kind of break off and migrate to other parts of your body. And yeah, you're up the creek without a paddle at that point. That's, well, actually, they're making some progress in cancer treatments, but damage to the genetic material is something. Damage to genetic material can be caused by chemicals also. A great majority of cancers are caused by chemical carcinogens rather than radiation. But, you know, if somebody sets off an atomic bomb down the road, if you're far enough away that you don't get vaporized or something, then it's quite possibly some cancer that's going to get you a few years later. Birth defects. What if it's not the genetic material in some random part of the body, like your pancreas or your brain or someplace like that? What if it's the genetic material in your reproductive parts that gets damaged? Well, that's what gets copied when you have babies, okay? And so if you alter the thing that gets copied, that alteration is going to get passed down to all future generations. Now, again, just like with cancer, most mutations are caused by some sort of a chemical mutanogen. But, you know, if you get exposed to a heavy amount of radiation, that can do it too. So, you know, a few mutations are actually beneficial. It's kind of a roll of the dice kind of thing. Occasionally, you get a beneficial mutation. A lot of times, they aren't really good or bad. You know, it's like blue eyes and brown eyes. I mean, you can see out of both of them. It doesn't matter that much. But more often than beneficial, you get harmful. A lot of mutations are bad for you. And so on the whole, they are something to avoid. Well, they aren't bad for you. They're bad for your children and their children, if they have children, and so on. So that brings us to the end of the course, except for, you know, review and that sort of thing. So it probably would have been better if we could do this face-to-face in person, but if you're watching this video, that means that there was some reason that we couldn't, and that's unfortunate, but I guess this was better than nothing. So good luck on the final exam and with your life after that.